We are now going to express the ideas behind finite automata more formally. We'll see how to represent finite automata either as graphs or tables. They are two representations of the same idea. And we're going to do a few proofs in considerable detail and learn some useful proof techniques, especially inductive proofs. An alphabet is simply a finite set of symbols. There are many examples. Two standard alphabets we see frequently are the ASCII and Unicode alphabets. An alphabet we'll use frequently is the binary alphabet, consisting of only the symbols 0 and 1. We'll also sometimes use alphabets of letters like ABC, and in the tennis example we use the alphabet of outcomes consisting of the letters S and O. Each protocol has a set of signals, and the set of all signals used by a protocol is also an alphabet. Strings are the usual data type you've seen in languages like C or Java. That is, a string is a sequence of symbols chosen from some alphabet sigma. The strings over sigma are those strings whose symbols are each members of sigma. For example, 011 is a string over alphabet 01. It is also a string over alphabet 0, 1, and 2. It just happens not to have any 2's. Unlike programming languages, which typically put quotes around strings, we're not going to do that. And even though strings are lists of symbols, we're not going to separate the symbols by commas or other separators. We'll just write down the strings like this. We use the expression sigma star for the set of all strings over the alphabet sigma. The length of a string is the number of positions in that string, and a special string is the empty string, which has length 0. We represent it by epsilon. For example, the language 01 star consists of all strings that can be made from the symbols 0 and 1. For example, epsilon, the empty string, is in this language. There are two strings of length 1, the strings 0 and 1, and there are four strings of length 2, and so on. Notice that we do not make a distinction between a symbol like 0 and the string of length 1 that consists of a single instance of that symbol, the string 0. We trust that context will make clear which we mean. Programming languages do make this distinction, so in C, for example, would put single quotes around the 0 if we meant the symbol or character 0, and would put double quotes around it if we intended the string consisting of only the 0. Languages are sets of strings, and they can be finite sets or infinite sets. The only limitation we place on languages is that there is some alphabet, that is, finite set of symbols, from which all the strings in one language are composed. Here's an example of a language L we're going to meet several times. Its alphabet is 01, and it contains all strings of 0s and 1s that do not have two consecutive 1s. So the empty string is there, and both strings of length 1. Of the strings of length 2, all are there except 1, 1, because that obviously has two consecutive 1s. 5 of the 8 possible strings of length 3 are there, as are 8 of the 16 strings of length 4. Here's a little puzzle for you to think about. For length 0 through 4, we see there are 1, 2, 3, 5, and 8 strings. Do you recognize the sequence? And can you extend it to strings of length 5, 6, and so on? And in particular, can you prove that your prediction is correct? Now we'll give the formal notation for deterministic finite automata. There is a finite set of states, and we usually use Q as the set of states. Don't ask me why it's Q, it just is. And there is a finite input alphabet. The traditional name for the input alphabet is sigma, again for no known reason. There is a transition function which we'll discuss on the next slide. It is the guts of the automaton, since it tells us how the automaton moves from state to state in response to inputs. The traditional symbol for the transition function is delta. One of the states in Q is the start state, and we designate it Q sub 0 typically. And some of the states are designated final states or synonymously accepting states. The final states are typically denoted F. The thing that makes the automaton work is the transition function. This function, usually denoted by delta, takes two arguments, a state Q and an input symbol A. It gives you back the state that the automaton goes to when it is in state Q and the next input symbol to arrive is A. The function delta is total. That is, it has a value for every state and symbol. There are examples of automata where we really don't want to continue in certain situations. For example, our tennis automaton did not have transitions out of the two states where one player or the other has won the game. To fix up such situations, we have to introduce a dead state. A dead state is a state that is not accepting and that has a transition to itself on every input symbol. Once you get to a dead state, you cannot leave it and you can never accept. So dead is a pretty good description of what is going on. We're going to use the abbreviation DFA for deterministic finite automaton. The deterministic means that there is a unique transition for every state and input symbol. We're going to meet non-deterministic automata soon, and there it is possible to transition to many states from one state on one input. Now, back to the matter of a dead state. Here's our tennis example, and you can notice that the two accepting states do not actually have any transitions out. So we add a dead state, and all the missing transitions go to that state. The transitions from the dead state are to itself on all possible input symbols. Like the tennis automaton, we can represent any finite automaton by a graph. The nodes of the graph are the states of the automaton. The arcs are the transitions. There is an arc from state or node P to state or node Q labeled by all the input symbols A such that delta of P and A is Q. For example, this arc would be present if delta of P and A and delta of P and B were both Q. We represent the start state by adding an arrow labeled start into that state, and we indicate final states by double circles. This is an interesting example of an automaton that processes text. The goal is to recognize that the string read so far ends in ing. The start state represents the condition where we have made no progress toward seeing ing. If, in that state, we next see I, we've made some progress, so we go to the state that says I was the last symbol seen. Otherwise, we stay in the start state because what we've seen so far is no help in seeing ing. Now, from the saw I state, if we next see an N, then we have made more progress. We go to state saw IN. If we see another I in state saw I, then we've not made progress, but neither have we lost ground. We may be reading a word like skiing with a double I. Thus, the transition from state saw I on I is to itself. On any symbol other than I or N, we go back from saw I to the start state. In state saw in, if we next see a G, then we win. We have just seen ing as the last three symbols, so we go to the accepting state saw ing. On the other hand, if from state saw in we next see an I, then the pattern in is broken, but a new pattern beginning with I has started, so we go into the saw I state. On any input other than I or G, including N, we have no progress at all, so we go back to the start state. And finally, from state saw ing, we can only go to state saw I if the next input is I, and otherwise we must go back to the start state. Here is an automaton that represents the simplest possible protocol for sending data. The program is in one of two states, ready and sending. It starts in the ready state. Eventually, it gets a signal that some data has been loaded into its buffer, and at that point it enters the sending state, where it does what is necessary to transmit the contents of the buffer. The receiver will send back an ACT signal when the contents are received, in which case we are ready to return to the ready state. However, if the receiver is down, we may instead get a local timeout signal that warns us something is wrong and the buffer must be retransmitted. This automaton is not complete. There are no final states because the automaton is designed to run forever without rendering a decision. Also, there are missing transitions. It is okay to ignore ACK or timeout signals if you're in the ready state, staying in the ready state. However, a data signal in the sending state is an indication of an error, so we might want to go to an error state. And the error state is a dead state, so we need transitions to itself on any of the three inputs. A typical question that is asked about protocols is whether you can get to an error state. We could, for example, make the error state be final, and then ask if the language of the automaton is empty. As we shall see, there is an algorithm to tell whether the language of a finite automaton is empty, a question we could not ask about programs in general. In this example, however, it is really easy to see that there is a path in the graph from the start state to the final state, so its language is not empty and errors are possible. For a running example, we're going to use this automaton. Its language is the set of binary strings that do not contain two consecutive ones. State A is where the automaton will be whenever the input string seen so far is good. That is, it contains no consecutive ones. And also, in state A, it does not end in a 1. Surely the state should be the start state, since when no input has been received, there are not two consecutive ones, and moreover, the input so far does not end in a 1. We get to state B when the input is good, that is, no two consecutive ones, but the last symbol seen is a 1. Notice the only way to get to B is to be in A and then to get input 1. C is actually a dead state. We are there whenever two consecutive ones have been received. We arrive at C for the first time from B, which you recall means the previous input was 1, and in state B we receive a second 1. Once in state C, we stay there because once a string has 1, 1, you can never undo that fact, no matter how many zeros you see. We can also represent automata by tables. Here's our example automaton for strings without consecutive ones, shown as a transition graph in the corner. And we also see a representation of the same automaton as a table. The rows each correspond to one of the states, and the columns correspond to the input symbols. We indicate the final states by putting a star next to their name, and the start state is indicated by an arrow. The entries of the table are the values of the transition function applied to the state that is the row and the symbol that is the column. For example, this entry is C because it is in the row for the state B and the column for input symbol 1, and we know that delta of B and 1 is C. There are two important conventions we're going to use. They let us know the types of things without declaring types. In particular, we can distinguish between strings and characters. We use lowercase letters at the end of the alphabet, W, X, Y, and Z, and sometimes U or V to represent strings. When you see one of these letters, you need to think, aha, that's a string. And lowercase letters near the beginning of the alphabet will represent single symbols. Again, we'll try to remind you at first, but you have to think single symbol when you see one of these letters. The extended transition function delta is a function that takes a state Q and a string W of any length, including 0, and tells us where the automaton gets to if it follows a path in the transition diagram from Q, where the arcs are labeled by each of the symbols of W in order. That is, we look for the unique path from Q whose labels form W. In some materials you will see a hat over the delta to remind you that it is the extended version. However, as we shall see, the extended delta agrees with the given delta when the string W is of length 1, that is, it is a single symbol. Thus there is not really a need to distinguish the extended and original deltas. The definition of the extended transition function delta is an induction on the length of the string to which this function is applied. For the basis, delta of Q and epsilon is Q. That is, if you're in state Q and no input symbols arrive, then you stay in state Q. For the induction, suppose the input string is WA. By our convention, W is a string of some length, possibly 0, and A is a single symbol. The inductive rule says that we first see where you get to from state Q on string of inputs W. That would be delta of Q and W. And then you see where you get from that state, whatever it is, on the last input A. In this example, 0, 0, 1 is split into W, which is 0, 1, and A, which is 1. Then we have to compute delta of B and 0, 1 and see where it goes to on input 1. Now 0, 1 is broken into a string W that is just a 0 and then an A, which is 1. So we need to compute delta of B0 and then see where we get to on input 1. Okay. But delta of B and 0 is A. See, right here. Thus, we can replace delta of B and 0 by the A, and now we have to say, what is the value of delta of A and 1? Well, that's B. Okay, so that's a B, and we replace that by the B there. And then finally, delta of B and 1, that's C. So that's our answer. Delta of B and 0, 1, 1 is the state C. As I mentioned, the extended delta sometimes is given a hat. However, we really don't need to distinguish the two deltas because they agree on single symbols. That is, if we want the extended delta for a state Q and a string consisting of one symbol A, formally we treat that string as the empty string followed by the symbol A. Then we have to compute delta hat of Q and epsilon, but we know by the basis rule that this is Q itself. Thus, delta hat of Q and A is the same state as delta of Q and A. In fact, I really cheated on the previous slide. I needed delta hat of B and 0. I just went to the table and looked it up as if it were delta of B and 0. Now we see they are in fact the same, so it was no harm, no foul. There are many different kinds of automata. We've seen only the deterministic finite automaton so far, but there are many others. But no matter what kind of automaton, its job is to define some language. We'll use L of A to denote the language defined by automaton A. For a deterministic finite automaton, the language it defines is the set of strings that may take the start state to a final state. Formally, the language of a DFA is the set of strings W such that the extended delta applied to the start state and this W is a final state. For example, consider our running example of the automaton that accepts strings without consecutive ones, and consider the input 1, 0, 1. It should accept this string because it obviously does not have consecutive ones. The start state is A, and if we follow the path labeled 1, 0, 1, we first go to B. Then from B we follow the arc with a 0. That leads us back to A. The third input is another 1, so that gets us back to B again. Since the path from A labeled 1, 0, 1 gets us to a final state, 1, 0, 1 is indeed accepted by the automaton. Now this expression is called a set former. It describes sets, and in particular we'll use it to describe languages. In this example, it's describing the language of the automaton that has served as our running example. The set former starts with a curly brace, and then an expression representing the things we want to put in the set. In this case, the expression simply says that the set consists of some strings W. We know they're strings because of our convention. The vertical bar can be read such that, and then there follows a description of what must be true for something to be a member of the set. In our example, we say that the string consists of zeros and ones and does not have two consecutive ones. Many important facts about automata that we might want to prove are of the form that two sets, typically languages or sets of strings, are really the same. We're going to prove that the DFA we've been playing with accepts the language I claimed it does, the set of binary strings without consecutive ones. So one set is the language of the DFA from our example, and the second set is the language consisting of all strings of zeros and ones without two consecutive ones. I'm going to spend a good deal of time proving this simple result because it will give you all the details of how one proves things about languages. In the future, I'm not going to be so focused on proofs, but I think it is important that everyone go through one of these proofs in all its gory detail. To prove two sets S and T are equal, we generally need to prove two things, that each is contained in the other. That is, we start by assuming W is a member of one, say S, and we use that fact to prove W is in the other, T. Then we start over, and we assume W is in T, and we use that to prove W is also in S. In what follows, we take S to be the language of the DFA we have been playing with, and T to be the set of binary strings without consecutive ones. First, we're going to prove that if W is accepted by this automaton, the one shown in the slide, then W has no ones. Okay, and the proof is an induction on the length of W. It turns out that if we simply try to prove this statement on the slide, we fail, and I'll point out in a few slides what goes wrong. A common trick for inductive proofs is to make a more detailed statement here than you really want because it makes the inductive proof work. Here we need to distinguish whether an accepted string gets you to state A or state B because we need to know whether or not the string ends in 1, even though the conclusion no ones is true in both states A and B. The inductive hypothesis will be in two parts. Part 1 says that if W gets you to state A, then not only is W good in the sense that it doesn't have consecutive ones, but it doesn't even end in 1. Part 2 says that if W gets you to state B, then W is still good, but it must end in 1. Remember, the induction is on the length of W, so the basis case is when W is the empty string, the only string of length 0. We're going to use bars around a string to denote its length. And now, let's prove part 1 of the basis. Delta of A in the empty string is indeed equal to A, but the conclusion is true since the empty string does not have consecutive ones. For item 2, things are a little trickier. It is false that delta of A and the empty string is B, but it is also false that the empty string ends in 1. However, an important principle of logic is that the statement false implies false is true. That is, whenever the if portion of the statement is false, then it doesn't matter whether the then portion is true or not. The statement as a whole is true. Thus, a statement like, if I am Superman, then I wear red undershorts, is a true statement simply because I am not Superman. You don't have to concern yourself with the color of my undershorts. The mathematical term for an if-then statement that is true because the if part is false is that the statement holds vacuously. Now let's address the inductive step. We assume that W is a string of length at least 1, and we assume that the inductive hypothesis, the statements 1 and 2 from the previous slide, about strings that get the automaton to states A or B, is true for strings shorter than W. Let's let W be XA, where by our convention A is the last symbol of W and X is all the symbols, possibly none, up to but not including the last symbol of W. Since X is shorter than W, we assume the inductive hypothesis for X. We're going to prove both statements 1 and 2 for W, which remember we broke up as a shorter string X followed by the last symbol A. Let's start with condition 1. That is, if delta of A and W equals A, then W is good. It has no consecutive ones, and it does not end in 1. How can you get to A by reading string X followed by symbol A? Well, look at the diagram. The only transitions into A are on input 0. That's this and that. So symbol A must be 0. That immediately lets us conclude that W does not end in 1. And furthermore, these transitions to A are only from A and B. Thus, X must get us to A or B. Now, regardless of whether X gets us to A or B, we can conclude, using the inductive hypothesis, that X is good. It has no consecutive ones. Thus w, which is x followed by 0, also has no consecutive ones, and it surely does not end in 1. Now for part 2. If delta of a and w equals b, then w is good and ends in 1. There's only one way to get to b. You have to be in state A, and the input has to be 1. Thus, if w equals x followed by a, then x gets us to state A, and the symbol A is a 1. We can therefore conclude that w ends in 1. We apply the inductive hypothesis to x, and we conclude that x not only has no consecutive 1s, but doesn't end in 1. Any occurrence of 1, 1 in w would either have to be at the end or lie completely within x. We know it doesn't lie within x by the inductive hypothesis. We know 1, 1 cannot be at the end because x does not end in 1, and a is only a single 1. We conclude that w does not have consecutive 1s. Notice that if we don't use this more complicated inductive hypothesis, where we distinguish between a and b according to whether the string x ends in 1, then we cannot make the inductive proof. If we know only that x gets us to a or b, then we might think that x gets us to state A yet ends in 1, in which case w, which would be xa, would have 2 consecutive 1s. But we're not done. We still have to prove that t is contained in S. That is, if S is a good string with no consecutive 1s, then it is accepted by the automaton. It is helpful to restate what we need to prove in its contrapositive form, which is logically equivalent to the original. The contrapositive of an if-then statement, say if x then y, is if not y then not x. We can see why this is an equivalent statement, since if y is false, it couldn't be that x is true, because whenever x is true, y is true. In this case, x is the statement that w is a good string with no 1s, and y is the statement that w is accepted by the automaton. The contrapositive is that w is not accepted by the automaton, then w is not a good string. That is, it contains 1, 1 as a substring. A deterministic automaton has exactly one transition from each state on each input symbol. Thus, any string w gets the automaton from the start state to exactly one state. So the only way w could not be accepted is if it gets this automaton to state C. Notice that the only way to get the automaton to C is for some string x to get it to B, and then for an input 1 to follow. Once in C, you stay in C, so anything can follow the x and 1. We'll call that y. That is, any string w that gets the automaton to state C must be of the form x1y, where x gets to B. We already observed that the only way to get to B is by a string that ends in 1, since the only transition into B is on 1. Thus x must be of the form z1 for some z. Thus w is really z11y, and we can conclude that if delta of a and w is c, then w is bad. That is, it contains 2 consecutive 1s. Now we introduce a class of languages called the regular languages. These are the languages that have a deterministic finite automaton accepting them. That means that the language is exactly the set of strings accepted by this automaton. Soon we shall see that there are several other ways to describe the regular languages, including by regular expressions and non-deterministic automata. While many common languages are regular, there are also many that are not. Intuitively, finite automata cannot count beyond a fixed number. Thus, they cannot do things like check whether they have seen the same number of zeros as 1s on their input, or check that parentheses are balanced in an arithmetic expression. For those tasks, we need more powerful mechanisms such as context-free grammars, which we will meet soon enough. Here is an example of a language that is simple to understand but is not a regular language. To understand what this notation is saying, we first need to know that an exponent I on a symbol is shorthand for the string consisting of I copies of that symbol. Thus, 0 to the 4th means the string 0, 0, 0, 0. Thus, we read this set former as 0 to the n, 1 to the n, such that n is equal to or greater than 1, or more verbosely, the set of strings consisting of n zeros followed by n ones for some n equal to or greater than 1. The strings of the language L1 are thus 0, 1, 0011, and so on. Here's another example of a non-regular language, the set of strings that are balanced parentheses. The strings of balanced parentheses are those that can appear in an arithmetic expression. For example, the string 0 of left paren, right paren, can appear in an expression like a plus b times c. Or this string can appear in an expression like a plus b times c plus d. Examples of strings that are not balanced are the right paren followed by a left paren. This is not balanced because no prefix of a balanced string can have more left parens than right parens. Obviously, there is no arithmetic expression that has this sequence of parentheses as its sole set of parentheses. Also, 3 lefts followed by 2 rights. It's not balanced because it has more left parens than right. However, regular languages are common. For example, in each language there is a format for floating point numbers, and this format can be quite complicated with optional e's or decimal points and strings of digits that could be empty. But in all programming languages I know about, the set of strings that represent some floating point number is a regular language. This is a very interesting case illustrating what finite memory means. We want to know if a binary number is divisible by 23. We're going to read the bits high order first. But if we have only finite memory, how can we remember exactly what sequence of bits has been read, since the sequence can grow very long? But there is a trick. We don't really need to remember everything about the bits read. It is sufficient to remember what the remainder is when divided by 23. Thus we'll have 23 states, 0 through 22. These correspond to the 23 possible remainders when an integer is divided by 23. The start state is 0 because we interpret the empty string as representing the number 0. That may be a bit of an assumption, but nothing else makes sense, and treating it as 0 makes everything work out right. State 0 is also the only final state, since we want inputs that leave a remainder of 0 when divided by 23. We're going to assume that things are working right after reading a binary string w. That is, w takes state 0 to the state that is the correct remainder when w is divided by 23. I'm using the C-style percent operator to denote the remainder. You can read the percent as modulo or mod, which is just another way of saying the remainder when divided by. The transition from each state I on input 0 is to the state that is the remainder of 2i divided by 23. To see why this works, we know that I equals 23a plus b. For some integer a and for some integer b in the range 0 to 22. That is, b equals I mod 23. Then 2i is 46a plus 2b. Since 46 is divisible by 23, 2i mod 23 is just 2b mod 23. That is, when we divide by 23, we can just get rid of the 46a. We know it will leave a remainder of 0. Thus, we can take the state b, which is the remainder, double it, subtract 23 if it is 23 or more, and that gives us the new remainder and therefore the new state. We never need to know what a is, and we never need to know I exactly. For the same reason, when a 1 arrives at the input, we can go from state I to the state that is the remainder of 2i plus 1 when divided by 23. For example, twice 15 is 30. So from state 15 we go to the state that is the remainder of 30 divided by 23, or state 7 when the input is 0. From state 11 on input 1 we go to the state that is the remainder of twice 11 plus 1 divided by 23. That's state 0. So whenever a string gets you to state 11, that is, the string leaves a remainder of 11 when divided by 23, that string followed by a 1 must be divisible by 23 and therefore must be accepted. Interestingly, another regular language is the set of all the binary strings that if we read the strings in backwards, that is low order bit first, they form a binary integer that is divisible by 23. And there's nothing special about 23. It could be any number in both this example and the previous one. So for example, 0110100 is in this language because when we reverse it we get 0010110, which has the value 46 in decimal, and 46 is of course divisible by 23. It is really tricky to design a DFA to accept this reverse language. However, there is a theorem, which we shall see soon, that says if a language is regular, then its reversal, what you get by reversing each of its strings, is also a regular language. The proof of this theorem will let us construct the DFA for the reverse language from the DFA we just saw.